Okay, we're gonna get started here. I'm gonna try things with the light on, despite the kind of flashy light, because I have feedback that some people it's hard to write when it's dark. So I apologize. It's hard because we either have a flashing light or it's dark and you can't take notes. So we'll try it with the light on today, and then see how things go from there. And also, thank you everyone for making it despite the awful weather. I appreciate it, even though it is recorded. All right, so to begin with, just a quick update on weekly quizzes. So how are things going? 246 of you completed quiz 1, attempt 1. So 50 some or 60 of you decided to just take that attempt 2, which is perfectly reasonable. There was a 74% average. This average actually interestingly climbed over time, so it seemed like people who did it right at the beginning, I don't know, maybe there was more benefit in waiting. And then now in the 20-ish that have completed attempt 2, we're up to 87. So as I mentioned, the first quiz may be like a little tricky, a couple questions, but it should be enough preparation for attempt 2. Shouldn't be as bad, because again, the questions are all closely related to each other, so I don't intend these things to be adversarial. These quizzes are really just supposed to be there to keep you engaged, make sure that you're getting key concepts. I've also had people ask about which textbook should I be using. Is there particular practice questions in one textbook versus another? So one unfortunate thing about applied machine learning, so a machine learning course at this level, is there's no perfect textbook. I know some of you may have noticed if you're reading, say, the Trevor Hastie et al.'s textbook, it's a little mathy, it's a little maybe more detail in the mathematical derivations than we go through, and that's the case, and same goes for most of the other textbooks except for maybe the deep learning book. So it's a little bit tricky. I don't want to say this is the best, this is the worst textbook. None of them are exactly the right level for this course. And so the important things to know is that what you need to know is just what's in the lectures. I'm not going to expect you've read all 3 of these textbooks that we suggest as recommended readings. And in terms of informal recommendations, I think people find that the Bishop book is maybe a bit more digestible than the other ones, and then later on the deep learning book. And in terms of practice questions, I have to say that the quizzes are going to be the best practice, and I will also release practice midterm questions. And I'm not going to kind of blanket endorse the practice questions in any particular book. And over time, I will release more practice questions in addition to just the quizzes. But just I think there's been some worry from people, whether or not they need to know all the material and all these different textbooks, and no, those textbooks are there as helpful external resources, but it's what's in the lectures is what you need to know for the midterm. Any questions on the quizzes? Logistical issues? Yeah, up to the top. Oh, underfitting. Yeah, for sure. So underfitting, and we'll actually talk about this again in today's lecture a bit more formally, but just to give you a quick answer. So overfitting is a much more common term you'll hear used. Underfitting is when we have a model that is not doing well on the training set or the test set. So underfitting is just a model that isn't good at all. So overfitting is when our model is kind of doing well on the training set but not generalizing to the test set. Underfitting is just when our model isn't even good enough to do well on the training set. So underfitting is basically just means that your model, you need to add more features. Basically the general idea, and we'll talk about this again more in this lecture, is you want to keep ramping up the complexity of your model until it starts to overfit. And then you want to kind of find that sweet spot where you're kind of just before you get overfitting happening. Because prior to that, your model's not complicated enough, so it's underfitting. Yes, this is a good point. And we'll formally talk about these things again today. Yeah. Yeah. That is a weird, so I can say, I mean, the correct answer there was neither, because it's not a standard situation. Having your training error be way lower than your validation, that is a signal that there's probably something wrong in your data splits. For some reason, your validation split is easier than your training split. So, yeah, there's no term for that, and that situation, you should never have such a drastic situation like that. So it's not like a usual case in machine learning. If your validation error is way better than your training error, there's something funky going on, and there's no recipe for that funkiness. It's probably a bug. Yeah. Oh, so like, in terms of, yeah, if you were, so again, this is one of those ones where, it depends on the task a little bit. So, in general, so what I can say is the only correct answer here is that if you run cross-validation, that will give you a sense of what is like reasonable ranges. So say you run cross-validation and you get a standard deviation in your validation accuracy of 5 points, and you get a standard deviation in your training accuracy of 5 points. That lets you know that if your training accuracy is 2.5 points better than your validation accuracy, you're not overfitting. It's within a standard deviation. But in general, there's no blanket answer, but cross-validation is your best friend, because you run a few cross-validations, say even just within your training set. That gives you a good idea of like what is, the fluctuation. If you're fluctuating a few points in accuracy, then you don't need to worry if your training and validation are off by a few points. Yeah. Yeah. Oh, okay. This is a great question, and I think, so I should also repeat these questions because, again, people who are listening on the lectures can't hear them. So the question is just, what, in terms of if we were looking at accuracy numbers, how would we get a sense on one, whether or not we're overfitting, and also just whether or not those are reasonable numbers? That is the topic of today's lecture, so. Cool, okay. So one other quick thing is I did just want to clarify something from last lecture. There was a post on the discussion board about this, and I do appreciate people raising points about typos and slides and confusion, but this was a particular one, which wasn't just a minor, it's actually an interesting point. So in our discussion of this linear discriminant analysis model, we talked about that in order to learn this, we have to estimate the covariance matrix from the data. And during lecture, I gave this equation here on the bottom, but with a typo, where this was a 0 instead of a k. So for one thing, I fixed this typo, but another tricky point here is that I talked about how we're getting what we call the maximum likelihood estimate for LDA, and in fact, this equation that I used in lecture, the corrected one here, has this -2. So we're getting the covariance. We're basically summing over all of our data points for each class and getting the square difference between that point and the mean. And if we were actually doing a proper exact maximum likelihood estimate, we wouldn't have this -2. So we do a -2 here because we have 2 classes. We add this as a correction, actually, to make it an unbiased estimator. It's a little bit outside the scope of this course, but this is the better thing to use. It's a tiny difference. It's just subtracting 2. This is actually what's in the textbook, and so this is kind of correct, but this is the maximum likelihood. So it's a subtle point. I won't penalize you on an exam if you used either of these two things. It's totally fine. It's a difference of -2, but it's just, this is the right thing to do, but if we're talking just about the maximum likelihood, it's actually this thing up here. So I do apologize for the typo and also for the fact that I called it the maximum likelihood when in fact it's a corrected version of the maximum likelihood. And there's a good explanation of all of this actually as a place where I'll point to one textbook on page 109 and around there in Trevor Hasty's book. Okay, so that's all for corrections, clarifications. Now getting on to today's lecture. So today we're talking about error estimation and kind of concerns regarding how we fix overfitting models, how we estimate how well we're doing. So pretty practical in contrast to the somewhat more mathematical previous 2 lectures. So we've been discussing classification, and for the most part we've been talking about it at a pretty abstract level. So usually just binary classification, we're assuming we have a simple input feature vector x, but it's worthwhile thinking about what classification really is in the real world. And so getting back to the first lecture, we talked about some examples. So examples like doing object detection, so trying to classify the objects in images, doing spam email classification, or trying to even classify, say, tumors or abnormalities in medical imaging. And when we move to these real-world classification problems, things aren't so nice and so straightforward as we've been discussing in class, and so it's worthwhile to talk about some of the practicalities, and in particular, practicalities surrounding how we evaluate and improve our models kind of in practice. So there's various different objectives that we have when we're doing classification in the real world. So one thing we have to do is we have to select the right model for the problem. So this is often called the model selection. So we have to choose, are we going to use logistic regression, or are we going to use linear discriminant analysis? We have to have good ways of testing the performance of a new algorithm. So how do we know whether or not the model we selected is actually doing well? And then we also need to have ways to evaluate the impact of how this model is actually going to perform in, say, a real-world deployed setting. And again, as I mentioned kind of informally in response to one of the questions at the beginning, the key thing we're trying to do here is really trying to get a sense of this curve. So this curve on the x-axis, we have some notion of model complexity. Now this is left somewhat vague right now, but you can think about adding more features makes your model more complex. For example, you might have some model classes that are more complex than others. So we've covered pretty simple linear models, but later on in the course we'll talk about deep learning. So deep learning model with thousands of parameters is more complex than a simple logistic model. And what we ideally want to do is we want to try out a bunch of different models that have different complexities. For each of these models, we want to get some estimate of what is the training error for this model and what is the validation error for this model. And then we really want to kind of sketch out this curve. Now, it's not always the case that people actually plot exactly this curve. Yeah. Yeah, it's left, if you want to be really formal, so this is in brackets there, degrees of freedom. So degrees of freedom is intuitively proportional to how many parameters you have in your model. Other natural notions of complexity include like information theoretic measures, which are also proportional to degrees of freedom. So like how many bits of information does it take to specify your model? That's the most kind of general version you could do, but here we'll think about it relatively informally as more parameters, more degrees of freedom. And then again, prediction error here is also left somewhat vague. You can think of this as being accuracy, or whatever your favorite metric is, and we'll talk about some particular ones in a minute. But yes, in general, what we're always doing when we're building machine learning models in practice is we're at least implicitly building this curve and trying to find this point where our validation error has started to go up. So our training error is always going to go down. As we make our model more and more complex, we can always fit more and more complicated training sets. But eventually, our model is going to start doing worse on the validation set, and what we want to do is we want to figure out this point here. Now, to begin with, we're going to start by focusing in on the y-axis. So today we're going to talk about two different things. One is how do we deal with getting an idea of our prediction error, so actually getting a good estimate of how well our model is performing. And then the end of the lecture, we're going to talk about how we can play around with the model complexity using a technique called regularization. So in estimating our prediction error, the first point that I want to make very clear is that once we move to real-world prediction tasks, it's not as straightforward as just measuring what is our accuracy. So we can't just say what proportion of points do we classify correctly, because in the real world, not all errors have equal impact. And different types of mistakes exist, and these different types of mistakes can have very different consequences. So a really classic example of this is you can think about incorrectly classifying that somebody has a tumor and recommending that they get chemotherapy is a very bad error. Whereas letting something through a spam filter, that's not so bad, right? So there are these real-world considerations about the kinds of errors we're making, and we actually want to take these real-world considerations into account when we're designing our error metrics. And the other important thing is, in addition to individual errors having different consequences and different types of errors having different consequences, so you can think that in the tumor example, it may be worse to miss a tumor than it is to flag that maybe there is a tumor here. So it's worse to have a false negative than it is to have, say, a false positive. But the other issue is that in the real world, our data is not balanced. So far, not explicitly, but somewhat kind of implicit in everything we've been talking about in these simple linear classification lectures, we've been assuming that there's a relatively balanced number of positive and negative things. But this isn't always the case, and in reality, oftentimes we have extremely imbalanced data sets. So spam classification is an example I seem to use all the time, but it's a useful example here because in reality, it's not that half of emails are spam and half of emails aren't spam. It's, for the most part, hopefully, maybe 99% of emails are not spam. And there's an important consequence of this because if we're talking about just the accuracy of our model, we're saying what proportion of classifications do we get correct? If 99% of emails aren't spam and we just predict everything isn't spam, then we have 99% accuracy. Because even if we don't even make any predictions, we just say, oh, everything isn't spam, well, we have 99% correct because 99% of things aren't spam. So when someone says to you, oh, look, my model has 99% accuracy, that is kind of a meaningless statement unless the data is balanced. And so one of the things we're going to talk about today is what are proper error metrics to use that actually account for data imbalance, and that also account for the different types of errors that we might care about. Any questions at this point? Okay, so to get a bit of a sense of what this actually looks like in the real world, we're going to use a few examples, and these are actually real published papers, for the most part from 2013, 2014. I'm just putting their abstracts up, and they're papers that are all about classifying trying to predict whether or not seizures are happening from EEG data. So this is a very interesting problem, and this is something people care a lot about because if we could do a really good job, say, classifying the presence or not presence of seizures in the brain from embedded signals, then there's ways you can actually have implants that can help prevent seizures before they occur. So this is a very real-world, actual application, and again, mostly papers from a few years ago. So in this abstract here, something called the application of intrinsic timescale decomposition to EEG signals for automated seizure prediction. If you start reading papers in ML and applied ML, they all have very nice mouthful titles like that. But here they say they have an accuracy of 95%, and they say they have a sensitivity and specificity of 99 and 99.5. And so it's like, okay, well, what does that mean? We just talked about how accuracy is not always the best thing. And so here they're talking about these different metrics. They talk about accuracy, which is just the number of correct, so true positives, so cases when there was a seizure and we correctly said there is a seizure, plus true negatives, so cases when there wasn't a seizure and we said there's no seizure, divided by the total number of examples. So accuracy is a very straightforward, classic metric that we all know. They also use two other terms here, one of which is the sensitivity, and one is what they call the specificity. So sensitivity in this case is the number of true positives divided by the total number of actual positives. So it's basically saying, assuming there was a seizure, what's the probability that I actually say that seizure is there? So this is an important thing in biology. You basically want to know how sensitive, it's kind of intuitive name, how sensitive am I to the presence of there being seizures? And then specificity is the true negatives divided by the total number of actual negatives. So this is basically telling us the opposite of sensitivity. It's saying, in some sense, how precise am I? So this is a particular example, and in this abstract, it's nice that they report these two things, sensitivity and specificity, because these give us an insight about the different types of errors that this model is making. Again, this model is doing pretty well. It's got 95 or 99 on pretty much all these things. But here, the reason why they're reporting these two different types of metrics, not just reporting accuracy, is because they really care about the difference between two different types of errors. These are called type 1 and type 2 errors. And just as a quick heads up here, there's a few different terminologies I'm going to use, like type 1 and type 2 errors, and sensitivity and specificity. And not all subfields in machine learning, in particular text, NLP, natural language processing, people have one set of language, and people who do applied machine learning for biological tasks have a different set of language. And so I'll flag that as it comes up. But here we're talking about what are called type 1 and type 2 errors. So a type 1 error in this example of, say, diagnosing a disease is that we classify the patient as not having the disease. Sorry, the patient does not have the disease, but received the positive diagnostic. So this means we have a false positive. That's type 1 equals a false positive. A type 2 error is a false negative. So a false negative here would be the patient truly has the disease, but it wasn't detected. And so when we're talking about sensitivity, sensitivity is really telling us how well we're doing at minimizing our type 2 errors, whereas specificity is for type 1. And then in spam, it's not just for biology. In spam, you could talk about this too. So a type 1 error for spam detection would be a message that is not spam is actually assigned to the spam folder. And similarly, a type 2 error is a false negative, so it is spam, but it makes it through. And again, this key point about not all errors being equal is that in different applications, we're going to have a different tolerance for certain amounts of type 1 and type 2 errors. And so you can see this plays out when we bring up another example of a paper doing a very similar task. Again, we're classifying seizures, doing seizure prediction using EEG data. And here they talk about how their model has a greater than 85% sensitivity and what they call a warning rate of 0.35 per hour. So here, what they're emphasizing, this model doesn't have the best sensitivity, so it misses, 15% of seizures, but it has a low warning rate. This is the point they're trying to make. So this is a model that is doing better at minimizing these false positives. On the flip side, here we have another one where they're playing up a bit more the sensitivity. So they're really playing up the fact that this model does a good job at minimizing these false negatives. So it's important that it can be difficult when somebody reports the performance of an algorithm to just straight up say one model's better than the other, because it might be better than the other in different circumstances. So depending on the type of implant you're giving people, it may be the case that for people who have seizures all the time, and these seizures are very extreme, that you're willing to tolerate some false positives because you really don't want these people to have seizures. But that might not be the case with all populations. Okay, so getting into just a bit more terminology here, we really have 4 different types of classification outputs. We have true positives, so cases where we made the right prediction, it was spam, and we classified it as spam. We have false positives, so this is where We classified it as spam, but it's not spam. This is called type 1 error. We have true negatives. So this is where we said it's not spam and it's not spam. And we have false negatives. So this is where we said it's not spam, but it actually is spam. And this is a type 2 error. And for simplicity, we denote these things by these M11. So what this means, M11, is that this means that the first number is the first number is the true. So 1 means that truly it's a spam, and then the next one means what we classified it as. So an M01 is that it's truly a 0, but we classified it as a 1. And our total number of instances, the total number of examples in our data set, is just the sum of all these types of things. So once we compute the true positives, the false positives, the true negatives, the false negatives, we sum all these things up, and that's our entire data set. Every prediction we make falls into one of these 4 categories. And if we're talking about just the raw error rate, that is just the number of false positives plus the number of false negatives divided by our total number of instances. So this is just the raw number, that's how many errors that we make. And then 1 divided by this gives us our accuracy. But again, this important point that I made earlier is that if the classes are very imbalanced, this error rate really doesn't tell us anything. Again, if we have a data set where 90% of things are from class 1, then we can get an error rate of 0.1 by just classifying everything as being in class 1. Now, if you're using most software packages for machine learning, if you're working in Python and using what's called, say, scikit-learn, will let you output this. This is a software package we'll have a tutorial on in the coming weeks. But also if you're using any other of your favorite packages like the R programming language or Stata or what have you, usually you can get an output that's called the confusion matrix. And this confusion matrix is something that is actually a fantastic resource that is very useful to output instead of just a raw summary of your performance. And what this confusion matrix is this is a summary of all the different types of predictions you're making. In particular, it's a matrix that tells you how many true positives you're making, how many false positives, how many false negatives, and how many true negatives. And the way it's usually set up is that on the Y, kind of the vertical split, is the predicted class, and then on the horizontal split is what the actual class is. And so this is super useful. I'm talking about this in the binary case, but you can also output kind of confusions for multi-class, kind of higher dimensional things. And it's very useful because you might say, oh, look, I'm always misclassifying points in class 3 as being in class 5, or vice versa. And so, again, it's useful to not just look at your raw error or your raw accuracy. It's very useful to actually see the kinds of errors that you're making. And as a minor point, the format for this matrix isn't always the same. Sometimes it's kind of the transpose of this, etc. Okay, any questions at this point? Yeah. Oh, yeah. So the question was just, what is the purpose of the confusion matrix? The confusion matrix is generally more of a diagnostic tool for you, rather than, sometimes you will report this, but usually you're going to report one particular measure, and I'll talk about a bunch of these kind of single numerical measures that summarize this matrix in a second. But this is more of a tool for you where oftentimes it's useful to look at this output because it's kind of in a nice visual way summarizes how many true positives, false positives, true negatives, and false negatives your model's predicting. So you could just output those 4 numbers, but most people find it easier and nicer to actually look at this kind of matrix table view of this data. Okay, so this is the confusion matrix. Really is this thing that's summarizing in some sense all the different types of errors or non-errors that we're making. But still, at the end of the day, when you're saying your algorithm is better than the other person's algorithm, You usually actually want to report some number that backs that up. And it's kind of hard to say, well, look, my confusion matrix looks better than your confusion matrix, because what does that mean? So in reality, we do actually report single numbers, but there's a bunch of different single numbers we report, and they depend on what we care about. So going over this again, I mean, we've heard about accuracy. Accuracy, very simple. It's just true positives, true negatives divided by all of our examples. Another really important thing is precision. So this is true positives divided by the total number of declared positives. So how often when we say this is spam, is that actually spam? The other thing is recall, which is true positives divided by total number of actual positives. So this is saying how often, of all the spam emails, how many of those do we actually classify as being spam? So these two terms have very, it's a one case where actually in statistics and machine learning we've named things in a reasonable way. Precision and recall are very intuitive. So precision means how precise is your model. If you have very, very low precision, then this means that your model's often classifying things as being spam when they're not really spam. Recall is basically telling us how many of the spam emails we're tending to miss. So if your model has a very low recall, then you're missing lots of spam. Your model could be really precise. You could have a model that every time, you could have 100% precision. Every time you say something is spam, it's actually spam. But you could have terrible recall, meaning that there's millions of spam emails that you miss. Now, that's probably not the thing you want for spam detection, but again, maybe if you're diagnosing diseases, you might want to have a trade-off like that. And you may recall that when we were talking about these examples from applications in detecting seizures, I used this term sensitivity, and you may have noticed that, wait a minute, isn't that sensitivity just the exact same as recall? And yes, that is true. So sensitivity is often used in medicine. So people will talk about sensitivity if you're reading a medical journal or a computer science paper that's applying things to a medical or a biomedical application. But recall is perhaps the more common term for general machine learning. And in particular in text classification, people are always talk about precision and recall, or information retrieval, spam classification, precision and recall. And then in medicine, it's sensitivity and specificity. And specificity is, remember, slightly different than recall or precision. Specificity is the true negatives divided by the total number of actual negatives. And this is something where you might care about in medicine, again, because you might want to know how many times when you say this person doesn't have cancer, they actually don't have cancer. And then there's also something called the false positive rate, which is exactly what you'd expect it to be. And now we have a whole ton of numbers, so what do we actually report? Well, one of my favorite measures to report, especially if you're working with imbalanced data, and the standard measure really in most of natural language processing, so applying machine learning to text data, is what's called the F1 score, or the F1 measure. This is also quite common in object detection, and this is a nice summary of the precision and the recall. And what is this? It's actually equal to 2 times the precision times recall divided by the precision plus recall. Where do we get this from? It's actually the harmonic mean of precision and recall. There's not going to go into details motivating exactly why we use this harmonic mean, but it's a really nice measure because it's very robust to imbalance in the data. And this is this measure where sometimes in papers they'll report the precision and the recall, but generally if you're doing a classification task where you have quite imbalanced data, which is again most classification tasks, the thing you're going to often report is the F1 measure. And one minor thing to note here is that this F1 measure is pretty hard to interpret. So what you have to do then is you can't just kind of say, oh look, I have an F1 measure of 0.45, my model's the best. You generally have to say, look, I have an F1 measure of 0.45, but if I were to just classify everything as being the majority class, that would have an F1 measure of 0.1. And if I was to use a logistic classifier with this simple set of features, that would be an F1 measure of 0.35. So really, once we start moving to these more advanced error metrics, which are better to use than something like accuracy, because again, they're better for dealing with the imbalance in data, you can no longer just report kind of raw numbers. Those don't mean as much to anybody anymore. What matters is how well your algorithm performs relative to some baselines. So you always have to have not just your method, but some sensible comparison point. And oftentimes what people will use is one comparison point is what happens if I just predict randomly. I just kind of randomly guess. How well do I do when I just guess the majority class? How well do I do when I use a very simple logistic regression? And how well do I do when I use my model? And obviously that's not always the exact set of comparisons you're going to make, but the important thing is that if you say my F1 measure is really good, you better be saying it's good compared to something else. And we call these the baselines. Okay, so getting into this trade-off between false positives and false negatives, so there's going to be one more really useful metric we'll cover, and then we're going to switch things up a little bit. So there's this really important trade-off between false positives and false negatives, right? Intuitively, these are kind of the opposite kinds of errors. So false positive is when our model is being not precise enough. We're saying all these things are spam, we're just saying everything's spam, when really spam is pretty rare. False negatives are the opposite. This is when our model is being kind of too conservative in its predictions. And these errors are very much kind of in opposition with each other, and you can play this out by actually doing a little thought experiment, and you can actually run this in code if you want. So suppose we trained 30 different classifiers. So you came up with 30 different logistic and linear discriminant, a bunch of different models. They're all slightly different from one another. And what we're going to do to make a classification is we're going to combine the output of all of those models. And in particular, we're going to say that we're going to order these models from model, say, 1 to model 30. And we're going to use a different threshold. So that's what this x-axis is here. And we're going to say that let's classify a point, say, as being spam, if the first 5 models, if we're using a threshold of 5, we need 5 models to vote that this thing is spam. If we crank our threshold all the way up to 30, we're only going to classify this thing as spam when all 30 models classify it as spam. So the important intuition here is that as we're cranking this threshold, we're using an AND function. So we're only saying that this thing is spam if all the models think it's spam. So here, this is what we do with just one model. This is taking the AND of 5 models, the AND of 10 models, etc. And intuitively, as we crank up this threshold, this is going to make our model more and more and more precise. Because basically we're requiring more and more evidence to classify something as a positive as we increase the number of models that have to vote yes on it. And what this looks like on this curve is that as we go over to the right, a number of false positives is going down, 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 down. So as we require more and more and more and more evidence to classify something as a 1, so as spam, we really decrease these false positive rate, but we crank up the false negative rate. Because now we're being so conservative. Once we require all 30 models to vote yes, it's really rare that we actually are going to classify something as being spam. And one useful thing to plot when we're considering, so we often consider this the kind of decision threshold. So we can aggregate different models in a different way. If our model outputs a probability of something being spam, we can choose what probability we have to see in order for us to actually classify as being spam. Maybe we want to be really conservative and only classify as spam when the model outputs a 95% probability. And as we change this threshold, we're trading off between the number of false negatives. So we increase the threshold, we increase the number of false negatives, decrease the number of false positives, And what we can plot as we're playing around with this threshold is how the trade-off between precision and recall changes. So you can see that if we're, say, getting a precision of 1, we can get a precision of 1 and keep the recall, or keep our precision at 1 as we change our threshold, but then at some point, as we increase the recall, we're going to start to pay a penalty in terms of precision. So this is this important curve we want to play around with, where we're going to want to be somewhere on this, and this is going to be somewhat application specific. Maybe we're happy being right here. Maybe we'd prefer to have a model that has 100% precision and the best recall we can do. So this kind of curve is often called the receiver operating characteristic. So this is an example of a naming in machine learning that is not very reasonable or intuitive. But the intuition behind what's called this ROC curve is that suppose we have 2 different classes. So we have the blue class here, we have the red class here, and we have our decision threshold. Right? So as we vary this decision threshold, where everything on the left we're going to classify as blue, and everything on the right we're going to classify as red, as we vary this decision threshold, we have a different number of true negatives, false positives, false negatives, and true positives. And this brings us back to a question in previous lectures, kind of, well, where exactly are we putting this decision boundary? What happens to the points that fall on the other sides? So these are different types of errors. But as we vary this threshold, we're going to get a trade-off between the number of true positives we have and the number of false positives we have. So there's other things we care about, but for now, we'll look at the true positives, so TP, on this axis, and the false positives, FP here. And again, we can vary this threshold in a bunch of different places and see what's our false positive rate, what's our true positive rate. We can get all these dots, and at the end of the day, we get a curve. And this curve is called the receiver operating characteristic curve. The different thresholds we use put us at a different point on this curve, and this curve is a nice characterization of our model. And an important thing to note here is that the diagonal on this ROC curve, if we had a model that did exactly this, that's what you get from random guessing. So random guessing is just going to, as we increase our false positives, we're going to increase our true positives by the same amount. So we really don't get any signal. Our signal is only how much our model is above this diagonal. And so in practice, how do you actually build this curve? Well, what you actually do is you train a classifier. This classifier outputs some score, say a probability, or there's some sort of decision boundary. You vary the threshold of this decision boundary, compute the true positive and false positive rates at all these different decision boundaries. You get yourself a curve. You then kind of smooth this curve out by taking what's called the convex hull, and then you get the ROC curve. Yep. On the validation set, but yes. You could also get, you probably want to get your ROC curve on the train set and the validation set. And luckily, you don't actually ever have to do this by hand. There is always going to be a thing in whatever programming language or sort of whatever stats package you're using, or scikit-learn in Python, that computes this ROC curve for you. But this is another place where, okay, this ROC curve is nice. This ROC curve, again, gives us a sense of the trade-off for a model. Yep. Yes, so there's, well, one thing you can do is that once you have this curve, it's a judgment call about where on that curve you want to lie, because it's a trade-off, right? Because as you go this way on the curve, your model is going to have, so as we kind of go to the left, our model is going to have less false positives, but also less true positives, right? So where you want, there's no way to say the perfect place on this curve, because that depends on how much you care about having false positives versus true. So if you really want your model to have really high recall, well, then you probably want to go all the way up here. But if you really care about precision, then you want to be way down here. But the fact of the matter is that you can't get any better, the best recall you can get for precision of, say precision of 0.0005 is right here. So this thing tells you kind of, this is the best your model can do. Now you have to decide where you want to set that threshold. Yeah. Okay. Yeah, so the question is, so here we're just varying the decision boundary, but couldn't we change, say, the architecture or something to make this curve better? And that is exactly what we want to do. But what is a better curve versus a worse curve? That's kind of the question, right? Because this curve characterizes the kind of how things change as we vary the decision boundary. So say we're trying to say, oh, my model has a better ROC curve than your model. What does that mean? Well, what we care about is actually the area under this curve. So that's what we want to optimize. Because if we had a perfect model, then we would have 0 false positives and complete numbers, so there's no labels here. We'd have 0 false positives and 100% true positives right away. So the perfect curve would basically be right up against the boundaries. And the better our model is, the greater area under the curve we're going to have. And so this is a very useful metric. So like the F1 measure, this is probably the other metric I use day to day the most. I probably actually use what's called the AUC, so the area under the curve, more than any other metric. And if this discussion of the area under this receiver operating characteristic curve, you're like, okay, this is all getting a bit abstract. Why is this the best metric to use? Well, it has a nice intuition. And the area under the curve can be interpreted as the probability of ranking a random positive example higher than a random negative example. So it's quite a nice summary statistic. It's pretty robust to data imbalance. There are an extreme imbalance data set where the AUC starts to break down, and that's mainly because actually getting this plot, getting this good curve becomes quite difficult. But in general, this is a very nice, very robust metric, and this is something you'll see a lot, so people talk about the AUC. You might also see people discuss the area under the precision recall curve, which is the same thing, but where we've replaced these axes with precision and recall here instead of FP and TP. They're pretty similar. The area under the ROC curve has this nice intuition. Yeah. Yeah. Yes, so this is a really good point. This is something where I realize now that I meant to add an extra slide on. It wasn't in previous editions of this lecture in this course, but I think it's a great point. So what do you do when you have multiple classes? So here we're talking about just binary classification. So there's generally what you do is you're thinking about kind of, if I have 3 different classes, I'm classifying O as, if the example is from class 3, I either got that wrong or I got that right. So I'm kind of classifying that example versus all the rest. But there's one important catch, which is that you might say, okay, so basically if I have 3 different classes, then I can kind of build 3 different AUC curves. One for how well I'm classifying class 1, one for class 2, one for class 3. And a tricky thing is that there's actually this subtle point about how you kind of aggregate these numbers. So one thing you can do is you could say, okay, I'm going to compute my F1 score or my AUC for each of my 3 classes, and then I'll average those 3. That's what's called macro averaging. But you could also do a different one where you just say, I'm going to say every time I made the right prediction, that's a 1, I got it right. Every time I got a wrong prediction, so I didn't predict the right class, I get it wrong. And then I could just build one AUC curve from that, and that's called micro-averaging. I will add a slide on this to the lecture because it's a subtle point that is worthwhile to review. Yes. Again, AUC, this is a great point. So AUC is a good aggregate measure of how good your classifier is. And so if someone was going to say, kind of without any context, which model's better, I would always say the one with the higher AUC. But if someone said, hey, this is a particular application where we really care about precision a lot more than recall, then I might say, okay, never mind. Let's just look at let's just look at the precision or the recall. So this thing is a summary of the trade-off between precision and recall. But you could have a model with higher AUC that in the particular region of the kind of this trade-off space that you care the most about is worse. And so the question there was just, whether or not AUC is always going to be better, or having a higher AUC is always better, say if you have two models where their AUCs cross each other. And like I said, it's context independent. The one with higher AUC is better, but particular applications might value only particular regions of this trade-off space. Any other questions on this? Okay. So throughout this entire lecture so far, I've been talking about classification, and in reality, classification is the place where a lot of these, tricky situations in terms of imbalance, etc., arise, and where there's a lot more choices in terms of how we're evaluating our model. But of course, there's also different evaluation metrics for regression, and so it's worth just quickly mentioning what are these different metrics. I'm not going to exhaustively list them all, but luckily things are a lot easier when we're doing regression, so when we're predicting a real valued number, not trying to classify into a discrete set. So some common examples for what people use, well, the two really common ones are the mean squared error or the root mean squared error. I'm sure people are familiar with these because that's what you use in your assignment. So this is just what's the average squared difference between your prediction and the true value. But the other one you'll see quite often is called the mean absolute error, and that is just what's the average absolute difference between your prediction and the error. And you might wonder, well, which one should I use? This is a case where there's no easy answer. So generally, people report the mean squared error, the root mean squared error is maybe a bit more common. But one thing with the RMSE, or the mean squared error, is that it penalizes larger errors more. So being off by 10 is more than twice as bad than being off by 5, because we're taking a square here. So this is a quadratic function, where this is the super intuitive thing. This just tells us, like, on average, our model's 5 points off, or 3 points off. Whereas a little bit harder to interpret this, but I wouldn't stress as much. I mean, oftentimes people just report both. It's pretty rare that model A does better on MSE, but worse on MAE, and then vice versa for model B. Like, almost always, one model is going to do better on both. So all of this discussion in classification, where there's all these different trade-offs and these different error metrics we can use, very, very important. Still good to keep in mind when you're doing regression, but in regression you can get away with just reporting one of these three, and no one's going to really fault you for that. Okay, now we return to this curve. So what we've been talking about so far is how to get a handle on our prediction error. Now, our goal at the end of the day is that we want to build a model that has the lowest prediction error on our training set, on our validation set. And so we're again trying to get a sense of this curve, where how does our prediction error change as we change our model complexity? So the first majority of this lecture was talking about getting a handle on our prediction error. So if we care about having a model that's really precise, we're going to put precision here. If we care about F1 score, we're going to put F1 score here. Yep. Yep. Oh yeah, that's a typo. I'll fix that. Good catch. So now that we've got a handle on the y-axis, we're going to talk a little bit about the x-axis. So again, our goal is to find the sweet spot on this curve. So we know how to measure this, but how do we play around with the model complexity? Now, here we're going to now bring back a little bit of statistics, because so far in this course we've been talking about model complexity in a pretty simple way, which is basically how many features does our model have. But unfortunately, we don't always have the ability to play around that much with our features. We'll talk about selecting and creating features later on, but there's a nice kind of bit more rigorous way to formalize when we're talking about model complexity and when we're talking about overfitting and underfitting. And in particular, we're going to talk about the notions of bias and variance. So some of you may have noticed these little things here at the top of this picture where we're saying models on the left, these are high bias, low variance models, and models on the right, so things that are overfitting, are low bias, high variance models. So now we're actually going to talk about what these terms mean and how we can build upon the ideas of bias and variance to tweak our model complexity in a statistically rigorous way. So what do these bias and variance terms mean? Well, here we're going to get a little formal and talk about this trade-off assuming a pretty simple model. So what we're going to assume, we're going to talk about regression now because regression is a bit cleaner than classification, but all these insights also hold for classification. So let's assume that we have some data set where we have our y's, the things we're trying to predict, some real number. And we're going to assume that these y's are some function, f, of our features, x, plus some error. So they're not a deterministic function, there's a little bit of noise, and this is a zero mean noise, and it has finite variance, sigma squared. So we're just assuming that there is some underlying model that predicts the y's from the x's. We don't know what this f is what we're kind of trying to approximate, but we're assuming that there is a good model to predict the y's from the x's with a bit of noise. Now suppose we learn any model, f hat, so we do some linear regression, some deep learning model, what have you, and we try to approximate these y's with our approximate model, f hat, and we want to get the error, what's our expected error, then this expected error can be decomposed into two things: the bias and the variance, plus this term here, which is just how much, tells us how much noise there is in the data. So we can't do anything about this sigma term. This is just, if in reality you can't do a good job predicting the y's from the x's, well then no model we learn is ever going to do well. But the thing we do have control over, the thing that actually does depend on our estimated f hat, is this bias term and this variance term. And so what are these two terms? The bias is how far off the mean prediction of our trained model is from the data point. This is basically saying a model has really high bias if it's kind of way off the mark on average. The variance is a different thing. The variance is just how much do the predictions of our model tend to vary about. So how wildly do our predictions vary? So bias is telling us, well, if our model is really biased, well then it's kind of always off. It's basically always off by a fixed amount. Or if our model is really high variance, when we change the input features a little bit, the output predictions can change a lot. And this is probably my favorite figure, one of my favorite figures in Introduction to Machine Learning, which is this illustration of bias and variance. So what does a high bias model that is low variance, this means we're off the mark. So we have bias, our average prediction is way off the mark, but we have low variance, so all of our predictions are close together. If we have a model, conversely, that has really no bias, so our average score is right on the mark, but we have really high variance, that means that, on average we're predicting here, but we're shooting all over the place. In the very worst case, we have a model that has high bias and high variance. That's a model where our average throw here in the dartboard is way off, and our throws tend to kind of vary all over the place. So in a perfect world, we would have a model that is low bias and low variance. We're low bias because we're hitting the target, our average throw is hitting the target, and we're low variance because our throws all tend to be clustered around the same spot. And if we come back to a plot from a few lectures ago where we talked about increasing the complexity of the features in our linear regression model, you might want to think about, so what does this mean in terms of bias and variance? So we talked about these plots in terms of overfitting, but overfitting and bias and variance are all the same sorts of thing. And in particular, as we increase the complexity of the features in our linear regression model, we were increasing the variance. We had this idea where we said, look, now that we're using, this was here, I think, order features that were order maybe polynomials of order 7 or 8, maybe even 9. And you can see that our predictions are varying all over the place. This is a really high variance model. And conversely, we went all the way down to this simple linear model with just linear features. This model has kind of high bias because it's pretty simple. So when we're talking about bias and variance, in terms of formal, overfitting is a model that has high variance. So variance is not necessarily a good thing because a variance means that our model is kind of going all over the place trying to fit all of our training points. So another way of saying your model is overfitting is that it has high variance. It's important here that this is kind of variance in this statistical sense. You know, the variance of your predictions is not always the best estimate if you just take the variance, but that's a minor point. The important thing is that variance in this bias-variance trade-off corresponds to overfitting. And bias, if you have a really, really biased model, then you're underfitting. So when we talked about at the very beginning of lecture, there was a question about kind of formally what is underfitting. Well, formally underfitting is a model that has really, really high bias. But I want to drive home the point that bias is not always a bad thing. And in fact, more often than not, what you're trying to control in your model is the variance, not the bias. Which is maybe seems a bit counterintuitive that you're like, well, why would I want a model that's consistently off the mark? But sometimes you're willing to pay that price of being a little bit off the mark to not have your model be really high variance and overfit all the time. So now the question is, what do we want to do to actually combat overfitting? So getting now to practicalities. So the one thing I've mentioned throughout this course that we can do when our model's overfitting is we can remove some features. We could try to use a simpler model. We could use something like linear regression instead of using quadratic discriminant analysis. But in reality, probably the most effective tool to control variance or to control the model complexity, again, a more complex model is going to tend to have higher variance. It's going to tend to overfit more. The one of the most important tools in the machine learning toolbox is what's called regularization. So regularization is a way of penalizing the complexity of your model. And we're going to talk quickly about two types of regularization that you're going to use all the time. So you're going to use this not in mini project 1, but almost certainly in mini projects 2 and 3. So the first type of regularization is called ridge regression, also called L2 regularization. Why ridge, I again can't tell you. And what ridge regression is instead of solving our usual linear regression problem, which is just this part here, we're adding a penalty term where we're not just trying to find the model that minimizes the squared error, we also are penalizing our model for how big the parameters are. So we're summing over all of our parameters, all of our weights in our parameter vector W, and we're taking the sum of the squares. So we're saying we want a model that has really low error and also has relatively small parameter weights. So this is our way of controlling the complexity of our model. Is our model is not allowed to have our parameters go really big and really small. They all have to be kind of clustered around 0. So we're penalizing what's actually called the Euclidean norm of our parameter vector. Now, luckily in the case of linear regression, adding this penalty term, we can actually still get a closed form solution. So if we do some algebra, we can actually find out that the closed form solution for what's called ridge regression, so L2 regularized linear regression, is given by this equation here. So it's basically our usual closed form for linear regression, but we've added this lambda times the identity matrix here. And lambda, I should say, this is something we set, so it's a hyperparameter like the learning rate, which controls how much we care about regularization. So if lambda is really big, then we're really going to penalize the complexity of our model. If lambda is really big, our model doesn't have very much ability to vary its parameter weights because it's going to incur a penalty. So this is a nice thing to do. We can get a nice closed form solution. A minor warning point is that unlike regular linear regression, this is now not invariant to how your features are scaled. So you have to do some normalization. Otherwise, your answers might change over time. And just to think about this in a slightly different way, basically what we're doing here when we're doing this ridge regression, so L2 regularization, is that we're taking our usual error for linear regression, so this is the sum of squared error, and we're adding a penalty term that is what's called the L2 norm. So that's why it's L2 regularization. This is the L2 norm. So this is just the Euclidean norm, the standard vector norm of our weights. So we're saying we want to minimize the squared error, but we're not allowed to have really big weights. And we can do the closed form solution. We can also very simply just do gradient descent. And so we can take the gradient of this here, and we get a new gradient update that is our usual gradient update for linear regression plus this penalty term. So it's pretty easy to actually do this with gradient descent. And if you want to apply L2 regularization to any other model besides linear regression, all you need to do is add this little penalty to your gradient. And this is really important because almost everybody uses L2 regularization all the time in machine learning. Yeah. Generally, no. So it's good to normalize what you're starting to regularize. In general, moving forward, it's good to normalize. Generally, not all models will be robust or non-robust to normalization, but it's a safe thing to do. That's a great question. So how do you normalize categorical data? In that case, there's no, we have a lecture where we're going to cover that, so I won't cover that now, but we'll return to that in a few lectures. Yep. Yes, this is a very great point, yes. So does this add bias to our model? Yes, that's exactly what we're doing. We are explicitly, on purpose, adding bias to our model. Now that we've added this penalty term, we're no longer going to perfectly fit the training data anymore. Our model's going to be biased. But we want our model to be a little bit biased so it's not so high variance. So interestingly, machine learning, a lot of it is adding bias, statistical bias, into your model. Now, what's the one other very popular type of regularization? We talked about L1 regularization, L2, and now there's also L1. This is also called lasso regression. Again, don't know why. But that's a name from statistics. Actually, I believe the author, Trevor Hasty, of the textbook coined the term lasso regression. Yeah, way at the top. Okay, yeah, that's a great point. Yeah, so how does adding this bias impact your recall and precision? Well, generally, if you're doing things correctly, so it's hard to say in general what's going to happen, but if you have one measure you care about the F1, or you care a lot about precision, what adding bias is going to help you go further this way on the curve. Basically, adding bias is going to help you hit a better sweet spot on this curve. So now you have another thing to play with. One thing you can think about is that adding bias, the more bias you add, the more simple your model is. the less bias you add, the more complex the model is. So a model with no regularization is very complex. A model with lots of regularization is very not complex. So I won't go into it, but actually there's very cool information theoretic interpretations of these things. So actually regularizing your model like decreases the number of bits of information that your model is allowed to kind of contain within it. Now, just quickly covering L1 regularization, this is very similar to L2. We're adding this penalty, whereas in L2 regularization, we were penalizing the L2 norm, so the Euclidean norm, or the square, the sum of squares. Now we're penalizing the L1 norm, which is the absolute value. So unfortunately, when we're penalizing the absolute value of all of our weights, well, now there's no more closed form solution. It's a little bit rough. It's actually not even differentiable. You can solve this using a quadratic programming problem. There's a lot of research on how to solve this. I'm not going to expect you to know how to do that by hand. I'm not going to cover it here. But the other thing you can do, so again, another way of looking at this is we've added this penalty term on the L1 norm to our error. You can actually do gradient descent even though this is not differentiable. So the absolute value is not a differentiable function. But luckily, this is a place where we can actually still get by. And in fact, what the penalty in the gradient update looks like is it's lambda, so how strong our regularization is, times what's called the sign function of our parameter vector. And this sign function is a nice simple function. If the value you input to it is greater than 0, it outputs a 1. If it's less than 0, it outputs a negative 1. And if it's exactly 0, it outputs a 0. Yep. So it's all element-wise. Good point. So it's the sign function applied element-wise to W. So thank you, yes. W was 1 minus 1, then the output of the sign function would be 1 minus 1. Yeah. So we're running a bit low on time. This is a quick visualization that I think is really useful for how ridge regression and lasso work. So suppose that this is different. So basically, every model that's on the same point of this contour has the same error. If we're doing L2 regression, this is basically saying we have to find the best solution that's within this ball or circle. So we'd end up here. If we're doing L1 regularization, this means we have to find the best solution that falls within what's called the simplex. And so one neat thing about L1 regularization is it actually forces individual parameters to go to 0. So L1 regularization will zero out some of your parameters, so it kind of selects features for you. L2 regularization will just give you small weights for everything. L1 will tend to give you zeros for some things and non-zeros for other things. So L1 is actually kind of a cool method, even though it's a bit more complicated to implement. And again, the key point here is that these penalties, these regularization terms, are introducing bias to decrease overfitting. And this is a really important idea in machine learning, that we actually often want to inject the right kind of bias into our models. And we like to call this the inductive bias of our model. So in machine learning, it's not about having models that are bias-free. It's about models that have the right bias. Because if our models don't have any bias, then all we're doing is memorizing the training data. So that's what machine learning is all about. Machine learning is all about trying to build models that have the right structure, have the right inductive bias. So we talked about linear discriminant analysis. The bias we have there is we're assuming everything's Gaussian. The bias we have in linear regression is we're assuming everything is linear. All these things are adding bias. So bias is the same as structure in the context of statistical bias in machine learning. And bias is what we want to do in some sense. We want to have the right bias and the right amount of it. All right, so that's all for today. Yep.
Text features, I was just want to clarify. So we have a list of 160 words,
Yep.
most common words, most common words in front. So now we have our X matrix. I thought that we were going to do, let's say, 4 features, let's say 5 features.
Yep.
Or 4, whatever approach we use. And the word count feature,
actually have 164 features. So, oh no, yeah. So the word count. This is a good point. What I mean by word count features is like for each of the 160 words, there's one feature that is what is the word count of this word in that. Yes. So,
I feel like it's a little. Our predictions are going to be heavily weighted towards how many.
yeah, and so you might find that using all 160 is not the best. yeah, yeah. That's part of the point. Yeah.
Okay, cool.
yeah, yeah.
I'm going to talk to my prof.
Yes, exactly. So if x is singular, adding regularization will allow you to still solve. Yes, exactly that. So actually, yes, you can solve a singular matrix. If you have a singular matrix with linear regression, you can add regularization to allow you to still solve.
小宇宙作业可以。
我也想找我写。Good question. It is not the same problem. Good question. I'm gonna walk over to office hours.
What do you say?
Yeah, I have office hours.
You know what? Okay, we'll figure it out. Oh, no, it's because you know when you did the thing,